maybe start here. Okay, can everyone hear me? Hopefully we can, because I forgot the microphone, sorry. Okay, and yeah, so let's start today. So last time we go over the postulates of quantum mechanics. I guess we can start with this four. So we have this four version of postulates of quantum mechanics. Postulate 1 talks about Hilbert space. Hilbert space represents space over every valid quantum state of your system, and then the state vectors. So quantum state is usually written as this unit vector Ksi, and which is also a complex vector. And postulate 2 says that how the system is transformed, and this is kind of derived from postulate 1 because the state need to stay uninom, so the transformation you can apply are all unitary operators U. And okay, then postulate 2 part, and then postulate 3 says about measurement. And in the most general form, measurement can be described by any set of operators, so you can have a set of any matrices, and they only need to satisfy this completeness relationship, some I, mi dagger, mi equal to identity. And if you have this, then you can calculate the probability of each outcome and the post-measurement state of each outcome. Okay? And so the probability, so to calculate them, basically you calculate this this number, this state mi psi. So you calculate this state, which is almost the post-measurement state, and so the norm of this state, norm square of this state is the measurement probability of outcome I. And if you normalize the state, then that's the post-measurement state of outcome I. Yeah. And then finally, we have postulate 4, which talk about what happens when you have multiple physical systems. So you have multiple physical systems, each with when they are isolated as Hilbert space H1, H2 to Hn. And when they are interacting, then the Hilbert space of the whole composite system is H1 tensor H2 tensor Hn. And if each system is prepared in a separate state psi I, then the whole system is in this state psi 1, psi 2 tensor to psi n. But this is not all possible state that the system can have. You can also have entangled state. And if you do unitary U on the excuse me, if you do a unitary U on the on one of the subsystem, then what you do is you do this huge unitary on this H1 to Hn space that that is you have a U on the eighth slot where you act on a subsystem A, and you tensor identity on every other slot. And similarly, if you do measurement on the eighth slot, then you are doing a measurement with the measurement operator being mi on the eighth slot, and tensor identity on all other slots. And I think in your next homework, you will do a small theorem, do a small proof to prove that this is also a valid measurement if a set of mi is a valid measurement. Okay. So those are the postulates. Then from the postulates, we immediately see one of the quantum effects, that is in quantum mechanics, there are unknown quantum states. So classically, in theory, you can always learn the state of your system, you measure it, and you learn it. But in quantum mechanics, the information can be stored in unknown direction, and if you don't know the direction, then you cannot really learn your state. For example, you might store your state in either 0, 1, so you can store one classical bit in either 0, 1 direction or plus minus direction. So if you store your state in 0, 1 direction and measure in 0, 1 direction, then you will recover your 0 or 1. And similarly, if you store your bit in plus minus direction, then you measure in plus minus direction, then you will get your plus minus outcome. But if you measure in wrong basis, so if your state was in 0, 1 direction and you measure in plus minus direction, then you will get this 50% outcome, no matter whether your input is 0 or input is 1. So you just get this outcome, and your input was erased. And similarly, if your input was plus and minus, then you measure in this 0, 1 direction, then you will also get the 50% outcome to be 0, 1 direction. And so your information on whether your state was plus or minus got erased. Okay. And then you might think that to avoid this, maybe we should copy our state. But there is also no coding theorem says that you cannot have an operator that copy any state for you. So if you have some state size, you want to copy it to some empty register 0. And so ideal copy operation will look like this. So you have a U on size 0 become 2 copy of size. And we say that we prove something even stronger. So we prove that 2 states cannot be copied with the same U if they are not orthogonal or equal. Okay. And yeah. So for example, in our previous example, you cannot copy both the 0 and the plus together with the same unitary. Okay. And yeah, and there is a quantum state tomography. This is when you have many copies, you can do something to learn your whole state. And now let's go back to an easier case. This is another quantum effect that was shown in the book. So if you if you want to just distinguish 2 quantum states, so you have some state psi 1 and state psi 2, and want to determine. So I guess the setup is like. If you want to be more careful, so setup is like there are 2 players. One is a referee that will handle either. So maybe let's draw something. Okay. So let's be a bit more formal. So you can think of this as a game where there is some referee, and you will give out states that's either psi 1 or psi 2 to a player. Okay. And then there is a player here, and the player receives psi 1 or psi 2 but doesn't know which, and try to answer. They try to get the answer, and it's 1 or 2. And the player wins if he is given he answers correctly. So if the state was psi 1, then he answered 1, and the state was psi 2, he answered 2. Okay? So then we are asking that if we have this kind of game, can the player win perfectly? Okay, and then we know that if the states are orthogonal, then the players can always win perfectly because you can do orthogonal basis measurement. Okay. You can always yeah. If the states are orthogonal, you can always do orthogonal basis measurement. You can just extend psi 1 and psi 2 to orthogonal basis and do orthogonal basis measurement that will perfectly distinguish psi 1 and psi 2. And but non-orthogonal state cannot be perfectly distinguished. And here we have some not quite totally proof example of saying 0 and plus cannot be distinguished. Because if you measure in, say, plus minus basis, then there is some outcome. So this plus outcome, you see the plus outcome, you are not sure you are getting plus or 0. And this is not a totally rigorous proof. And now we start doing the totally rigorous proof. So we want to distinguish quantum states. We want to say you have any two non-orthogonal quantum states, then they cannot be perfectly distinguished. And so kind of do this game, and want to say the player cannot answer perfectly. So you cannot have when you given psi 1, always answer 1, and you have psi 2, you always answer 2. And here we do something. First, we do something is I guess it's not really a generalization, but we formalize our player. So we say the player only answer 1 and 2. So we can really just formulate the player as a 2 outcome measurement. So player just do a 2 outcome measurement M1 and M2. And when the player get the measurement result M1, he answer 1. And the player get the measurement result 2, he answer 2. Okay. And so this is the player. This is the player now. Player is formulated as these two outcome measurement n1 and 2. And now I want to say no matter what n1 and 2 you pick, you cannot have them perfectly distinguished psi1 and psi2. And now we write down in equation what we mean by perfectly distinguished. So if we are given psi1, then you want the answer to be n1. That means the probability if we are given psi1, then the measurement outcome being n1 should be 100% probability. It should be 1. And so this should be so this one should just come from then the other one. So this one will also imply that from the completeness of the measurement or just the probability sum to 1, also have that if the input is n1, then the probability of outcome being n2 should be 0. Okay? And similarly, when your input is psi2, then the player should always answer n2. So probability of answering n2 should be 1. And this thing also implies that when the input state is psi2, the probability of answering n1 is 0. Okay, everyone okay with the formulation? This is just so up until here we are just trying to put our problem description into math. So we have this kind of a two-player game where referee give psi1 and psi2, and the player want to answer 1 and 2, and I guess we can have this a bit better, and so more like an interactive picture here. So the player will answer. So this is answer. They will send answer 1 and 2, and and then the referee will check whether the player get is correct or get is wrong. Okay. So again, kind of look at this, and we just model our player with two outcome measurement n1 and n2. Okay. And we say we can characterize what we mean by win perfectly. Win perfectly is always get a correct answer. When the input is 1, you answer 1, and when the input is 2, you answer 2. Okay, and after this, then we can start derivation. Okay, and so I guess important part of the derivation is that so this is basically the only thing we do. We say psi1 and psi2 are not orthogonal, so we write psi2 as a linear combination of psi1 and something perpendicular to psi1. Okay, and I guess psi2 can always return as this, but what's important here is that there you have two matrices. Okay. Yeah, I should have different colors. So I guess let's do underline here for me to remember put this thing. Okay. So the only thing we do in this proof is basically this paragraph. So we write psi2 in a linear combination of the psi1 component and some other component that's perpendicular to psi1. And from psi1 and psi2 being not orthogonal, we know that the component on psi1, so we say psi2 is on A psi1 plus B psi1 perpendicular. And from psi1 and psi2 being inner product being non-zero, we know this A is not zero. Okay, so this is the only important thing here. Okay. And then from here, we can just plug in this relationship into this 4 equation and get some contradiction. Okay. So suppose we have this and we also want to have this, then we will arrive at a contradiction. Okay. So we know that a squared plus b squared equal to 1 because psi2 is normalized. So a is not 0 and a is not 0, so b is between 0 and 1. Okay. And I guess here should be b can actually be 0, so greater or equal to 0. Yeah. And now we have n2 psi2, so we're looking at this equation and we calculate what's m2 psi2. And 2 psi2, now we write psi2 as our psi1 and the psi1 perpendicular is a and 2 psi1 plus b and 2 psi perpendicular. Okay. And but now we know this thing is 0 because it's this term. we know this term non-square equals 0, so it's just 0. We have two things that's equal to 0. N2 psi 1 equals 0, and N1 psi 2 equals 0. Okay, so we start with this, then psi right psi 2 are the psi 1 psi 1 and psi 1 perpendicular, but we know psi 1 N2 on psi 1 equal to 0. So this term is 0. Then we have this thing equal to Bn2 on psi 1 perpendicular. And but now we know this thing has non-square 1, but this thing should yeah. So now we take the non-square of both sides. Okay. So the non-square of this side and it's M2 psi 2, and we already know it's non-square is 1. Okay. So non-square of this side is 1. And but what about the non-square of this side? Non-square of this side is B1 square. And non-square of this psi 1 perpendicular and with N2 dagger N2 in the middle. Okay, and now we just show that this part is less than 1 because we can add in an extra term. So now we we add the extra term that's this psi 1 perpendicular N1 dagger N1 psi 1 perpendicular. Okay, and this is obviously greater or equal to 0 because this thing is just N1 and psi 1 perpendicular squared. Okay. Yeah, so this is the non-square of some vector, so this thing is greater or equal to 0. And so we add some positive term, and this becomes something larger. I guess it will also multiply with b squared. Okay. But anyway, we add this, and because they are both sandwiched with psi 1 perpendicular, so we can just add our ny psi 1 in the middle. Okay. So add this extra term here. And why do we really want to add this extra term is because now we use the completeness relation to have that N1 dagger N1 plus M2 dagger N2 is just identity here. Then so the middle part is identity, then we just have the non-square of psi 1 perpendicular. And I guess we didn't quite say, but psi 1 perpendicular we assume it's normalized, so its non-square is 1. So this thing is just b squared. But importantly, we have b squared. I guess this part we don't really need, so that's I have let's erase this part. We have no, b is less than 1, so no, b squared is also less than 1. Then in the end, we have 1 is less equal to 1 is contradiction. So we see that what we want here and psi 1 psi 2 being perpendicular cannot coexist. So those two will lead to contradiction. So you know that, well, if this is true, then those cannot be true. Okay. Any question with the derivation? No. Okay, and this is a distinguishing quantum state. And then now we go a bit off book to go to talk about different things. So this is a first part I want to talk about today. Then the second part I want to talk about directions in a qubit. Yeah. So this is a Bloch sphere and a Pauli. And we are going over a little weird ordering of the book. So we are actually going back on the book. So this was on chapter 1 of the book. Okay, but anyway, I think it's better to talk about it here. So this is a way to visualize 1 qubit. Okay, so we keep talking about measurement directions, and this picture kind of give you a direction of a qubit, and it also tells you about the XYZ. Okay. So this is this sphere is a ball with the radius 1, and the sphere will represent any 1 qubit state. Okay, and I guess here we start with derivation. So we have any 1 qubit state side is some A0 plus B1, and for complex number A and B. And first thing we do is, you think, I guess we recount our number of variables here. So we write them into real variables. So remember, A is a complex number, so complex number has a real part and imaginary part, so this is a two real variable, and I guess let's do the counting here. So it's a two real variable, 2 plus 2 real variable. I guess that's right up here. So A, B, so that's 2 plus 2 equal to 4 real variables. Okay, and but state quantum state don't really have a full degree of freedom because it also have this constraint here. Okay, so it's a four variable with one constraint. You also have a squared plus b squared equal to 1, which if you write down actually means imaginary part squared plus the real part squared plus the imaginary part squared plus the real part squared sum to 1. Okay, so it's a 4 real variable and 1 constraint. So in total we have 3 variables. Okay, to describe a quantum state. And yeah, so this is a way to describe these 3 variables. So we have this 1 constraint here. So a squared plus b squared to 1. So we write it. We can write a and b as a cosine something plus. Sorry. So the norm of a we know is we can write it as a cosine something, and norm of b is sine something. Okay. So we write a and b in basic polar coordinate. So if we write a and b, they are known as cosine something, sine something. They auto satisfy this constraint. So you have a cosine something and a sine something, and we have a theta over 2 because it will fit our sphere picture better. Okay, so cosine theta over 2, sine theta over 2, and then the remaining part is we have the face of A and B. Okay, so I guess I should really write here A equal to RA and EI theta A, and B equal to RB EI theta B. And from this constraint we have this RA norm of this RA should be cosine something, RB should be sine something. And we still have a theta and a theta b can be whatever free variable, and so now we have this gamma as theta a, and we can also have another phi for theta b, but to make it be nicer, we have the difference between theta and theta b as a phi here. Okay, so this is the same amount of information, just different writing. So we take all this theta a part as the global face of the whole vector, and then we have EI phi here. Okay, and yeah, so now we have this real variable gamma, theta, and phi. Phi is the phase between A and the phase difference between A and B, and theta is tells us the norm of the norm of A and B. Okay, and but we still need to get rid of one more variable because we will get a sphere. A sphere is a two-dimensional object. Is the surface of this ball, and so a sphere is parameterized only with only 2 variables. Okay, and so the other variable we can get rid of is actually this EI gamma. Because as we will see later, EI gamma is what's called a global phase. So it's a phase vector, meaning that it's some EI gamma with real gamma that multiplying on the whole state. And in fact, a global vector will prove later that a global phase vector on any quantum state doesn't change its property. And there are a bit more detail to talk about this now, but for now, let's just assume that this doesn't change anything, and we ignore this. So our psi can be really written as this cosine theta over 2 0 plus e to the I phi sine theta over 2 1. Okay, and we have some theta and phi. And if you think about what range theta can be, so theta can, so you want this cosine square and the sine square to become one is the cosine and the sine to make a and b range from 0 to 1. Then the angle here should be range from 0 to pi over 2. So theta over 2 should range from 0 to pi over 2. So theta should range from 0 to pi. And then this phi can just be anything from 0 to 2 pi. Because, EFI can be 0 to 2 pi is all different. Okay? I guess one of them should be, if you want to be very precise, because 0 and 2 pi is the same, so let's say it's less than 2 pi, between 0 and 2 pi. And but here 0 and pi are different. Okay, and from here then we can map this theta and phi to something on the sphere, and it's mapping on this mapping with this spherical coordinate. So any point on the sphere can be written as some coordinate theta and phi. And okay, so for example, this point here, we say is coming down from the z-axis with some angle theta, and then this projection has angle phi from x-axis. Okay, so from this spherical coordinate, you can see that theta can range from 0, so with this positive z pole, to pi down here at the negative z pole. And phi can be this whole circle around xy plane. So phi can be from 0 to 2 pi. Okay. And so we can map any point, so this is our way to map any vector onto a sphere. So write your side, our side as this cosine theta over 2, 0, and EFI sine theta over 2, 1. And from those, now we have the theta and the phi, and we plot the point exactly the same point with the theta and the phi as a spherical coordinate on this sphere. Okay, so far okay, but actually this is not too important, but I guess it's nice to know this formula. So this formula here is the powerful and dirty formula for point on the Bloch sphere. Okay, so this is a definition. You can always use it to map from Bloch sphere to a state or state to a Bloch sphere. But really, this is not too intuitive. You might think, okay, we do a lot, and why do we really want to make on this weird sphere? Okay, so now let's talk about something more interesting. Okay, so something more interesting about Bloch sphere is that after we do this mapping, and so if we define this way, and this has many nice properties. And the first property is that the XYZ axis on the Bloch sphere will correspond to our three poly matrices, poly sigma x, sigma y, and sigma z. And this is really why they are called sigma x, sigma y, and sigma z. Okay, so how they are related to them. And first, yes, we didn't say. Okay, I guess here I should say different thing. Okay, so we have sigma y, sigma and sigma z, and then first thing I want to say here should be eigenvectors. Okay, eigenvectors. So remember, well, sigma y, sigma z, sigma x, sigma y, and sigma z has their eigenvectors. And the first thing I want to see about this sphere is that those poles, the poles along x-axis, y-axis, and the z-axis, they are exactly the three eigenvectors of x, y, and z. Okay, and so if you do the mapping, then this point x-axis will be the plus state, and this point will be the minus state, and which are the plus eigenstate of sigma x, and minus eigenstate of sigma x. And this point is 0, which is the plus eigenstate of sigma z, and this point will be 1, which will be a minus eigenstate of sigma z. And this thing is, well, I said we type plus I here, but this will be also the plus eigenstate of y and the minus eigenstate of y. And I guess in our notation, this will be y plus and y minus. Okay. So yeah, so the axis, those three axes are corresponding to sigma x, sigma y, and sigma z. And the first thing we think is that the eigenvectors are the point on those axes. And here is an example with calculation. So we have theta equal to pi over 2 and phi equal to 0. And so theta equal to pi over 2 will rotate z to here, and phi equals 0, so it just stay here. This should be this plus stay here. And if you do the calculation with the formula, then cosine pi over 2 divided by 2 cosine pi over 4, 0, plus sine pi over 4, 1, and with phi equals 0, so we don't have e to the I phi term. And this will give us well, cosine pi over 4 equal to sine pi over 4 equal to 1 over square root 2. So this is 1 over square root 2, 0, plus 1 over square root 2, 1, and this equal to plus state. Okay, so we see that on the plus state this works out. So this point is the plus state, and this indeed is the plus eigenvector of sigma x. Okay, and so this is the first correspondence between Pauli matrices and bloch sphere. And second thing is we stay with our proof that the unitary operator, so the sigma x, sigma y, and the sigma z, yeah, so those three operator, when you apply on state, then you will rotate the sphere. Okay, so what do we mean is if we do this operation, so we take any vector, any vector on the sphere, which is a 2-qubit state, and say we apply some sigma I. Okay, so we can think about this transformation. So we take any point on the sphere and change it to sigma I times that vector, and well, this is still a 1-qubit state, so that will be also a point on the sphere. Okay, and turns out this sigma y, sigma y, and sigma z will be doing rotation around x-axis, y-axis, and z-axis with angle pi. Okay, so sigma x will do this pi rotation around x-axis. Okay, and so what does this mean? This means that say this y plus point will rotate pi around x-axis, so it will become y minus point, and then this 0 ket point will rotate pi to this 1 ket. And then if you have some weird point, say around here on the sphere, then it will rotate pi point to be somewhere here around the sphere, etc. Okay, and yeah, similarly, if you do rotation around the z-axis, then you do sigma z, you will rotate around the z-axis. So this plus x will get rotated to minus here. Okay, so yeah, sigma x, sigma y, and sigma z are rotation around x-axis, y-axis, and z-axis. And then we have a bit of a generalization here. Actually, any unitary operator is rotation on the sphere, I guess plus on face. Okay. But in particular, x, y, z rotation around x, y, z. Okay, and yeah, and yeah, and here we have something that we already taught. That we say that 0 and 1, these 2 points, they are the eigenvector of z, so they are here, 0 and 1. Okay. So now we go to a tricky part of the bloch sphere. is that this is a part that will get you confused if you're not careful. Is that the geometry is different from the geometry of Hilbert space. Okay? So there are two different geometry. So remember, Hilbert space we say it's an inner product space, and it has all the direction and the angle, etc. And this look the block sphere look like something in a three-dimensional space. So there is also some geometry, and we do rotation and stuff. But the geometry is different. What we mean is that just look at this 0 ket and 1 ket. Okay, and so in Hilbert space, 0 ket and 1 ket are orthogonal. Okay, so we say in Hilbert space, in Hilbert space, 0 and 1 are orthogonal. So 0 and 1 equal to 0. They are orthogonal vector, and you can also think orthogonal vector like this. You have one vector in this way and another in this way, and they have a 90-degree angle. But if you look at the block sphere, just look at the 0 vector and the 1 vector. They are not orthogonal. They are on the same line. Okay, so 0 vector is the 0 ket point is here. You can think, I guess this is technically a point, but you can also think it as a vector from the origin. Okay, so you have this 0 ket vector from origin to here, and this is 0, 0, 1 vector, and the 1 ket vector is here, is down here. It's 0, 0, minus 1 vector, and these vectors are not orthogonal on block sphere. Okay. And yeah, so this is something to be careful. Block sphere has many representation, but the direction of the vector here doesn't represent it doesn't represent the direction in Hilbert space. In particular, the angle between vectors on block sphere is different from the angle of vectors in Hilbert space. Okay. So yeah, this is quite important. Don't miss this out. Okay, and so this is the geometry of block sphere, and then one thing is then there's one more thing about block sphere is now we go back to kind of this XYZ. So we know the XYZ direction corresponding to sigma y, sigma z, sigma x, sigma y, and sigma z. And actually, any direction of the block sphere just represent something, just correspond to something in the physical universe, corresponding to our real world XYZ three-dimensional space. Okay, that is you can use a block sphere to represent the spin direction in our real world. Okay. And so here is a bit of a generalization about our XYZ thing. Okay, so so we think about a point on the block sphere represented by now back to the Cartesian coordinate or XYZ coordinate. So any point on the block sphere is a direction, and the direction can be it's a unit vector, so it can be seen as a directional vector. But anyway, it's a vector with three components XYZ. So that vector we have a three component called nx, ny, and nz. Okay, and nx, ny, and z if you return as a spherical coordinate, and you can do this transformation, which hopefully you learn in high school. Yeah, but anyway. So there's something really funny we can do is we can define from this block sphere we can define a poly of any direction. Okay, so before we have polys that only three polys: sigma x, sigma y, and sigma z. There are three matrices. This is a 1 1 matrix minus I matrix and 1 minus 1 matrix. Okay, and but in fact we can generalize the direction the definition of polymatrices to I guess it's weird to call them polymatrices, but anyway, you can generalize it to define 2 by 2 matrix in any direction x, and y, and z, and it's written in this way. So it's the inner product between this three-dimensional real vector with your Pauli matrices. And what does this mean is that you have three matrices summing together. So you have nx, which is a number. So I guess the definition is a bit confusing here because of how we write things. I should probably write big X, big Y, big Z here. So remember those three things. So nx, ny, nz. So those are real number. And then we have sigma x, sigma y, and sigma z. Those are 2 by 2 matrices. Okay, and yeah, so we have, I guess now it's a bit more clear about what is a weird sigma vector. So it's a vector of 2 by 2 matrices. Okay, it's a bit of a loaded notation, but anyway, what's really important now is we define this thing as the summation of these three matrices. So nx times sigma x, which is equal to this matrix, ny times sigma y equal to this matrix, and nz times sigma z equal to this matrix. Okay, and so we can define this matrix, and you will become, you write it back to, so well, you can write it as nx, ny, nz, and then you can use those things to write it then back to cosine theta, this theta and phi, and you have this nice form as cosine theta e to the minus I phi sin theta e to the I phi sin theta and minus cosine theta. And let's just check a little bit. So on the diagonal here, you have nz and minus nz, so that's just cosine theta and minus cosine theta. And these generalized Pauli, they have nice properties. So they are really like Paulis. In particular, they are like Pauli because they also have eigenvalues plus minus 1. Okay, remember a lot of properties of Paulis are derived from having eigenvalue plus minus 1. For example, this means that this matrix is Hermitian and unitary for any vector here. Okay, and yeah, we can have a nice example of next example here, which is a matrix that we already know a lot. That's the Hedema matrix H. So this H should be 1 over square root 2, 1 minus 1 is 1 over square root 2 sigma x plus 1 over square root 2 sigma z. So you can see it's over diagonal here is sigma x, and diagonal here is sigma z. So this thing is 1 over square root 2 sigma x and 1 over square root 2 sigma z. So its coordinate is n hat. N vector is 1 over square root 2, 0, 1 over square root 2. And it's phi equal to 0 and theta equal to pi over 4. Okay, so we're back to here. So the Hedema matrix is has a direction here. So it's somewhere between in the middle point between the x-axis and the z-axis. Okay, and I guess we need to say a little more. So for this thing, probably here. Okay, and for these Pauli directions, so the bloch sphere interpretation of Pauli matrices all applies here. So in particular, we have the eigenvectors and eigenvector and rotation. Okay. So we have that these two property will also satisfied by those n sigma. So means that the two eigenvectors. So it has two eigenvector with eigenvalue, each with eigenvalue plus 1 and minus 1. And the plus 1 eigenvalue will be this point n hat. And minus 1 eigenvector will be the minus 1 will be the totally opposite direction. Okay, so here we have a drawing for assuming you have nx, ny, nz here, Okay, so and this is the axis on this three-dimensional space, and let's try to draw a straight line, and it has 2 points here. So we have this plus n vector here, and minus n vector here. Okay, so those 2 points will be the 2 eigenvectors of this direction, and also if you apply and if you apply this matrix, just this matrix, you will be rotating around this axis, this this nx, ny, nz axis with 180 degree. Okay, and with this property taught, we can go back to our Hedema example. So Hedema, it has 2 eigenvectors, and we didn't talk about eigenvector of Hedema, but you really want them. They are those 2 vectors: cosine pi over a, sine pi over a, and minus sine pi over a, and minus cosine pi over a. And yeah, there will be the vector around the vector with this point and this point in the middle of xz axis and in the middle of xz axis. And then the more interesting thing that we already know is when you do this rotation around Hedema axis. So the rotation around Hedema axis, you rotate around this middle point of x and z with 180 degree. And what happens is you see that then you rotate 180 degree, then you will rotate this x vector, this plus x point to this plus z point, and you will rotate this plus z point to plus x point, and similarly you will rotate this minus x point to minus z point, and it will rotate minus z point to minus x point. Okay, so you see that exactly because the Hedema is the rotation between x and z, you will swap between the row of x-axis and the z-axis. Okay, so this gives us a bit of an interpretation of the Hedema matrix. And I guess this is all I want to talk about. The next time we will start with a bit more quantum information. So, I guess we can say a little bit. And yeah, so we have those direction. I guess we didn't finish this. Okay, so we talk about bloch sphere, and any point or any direction of bloch sphere correspond to some generalized poly. And now let's go back to this spin direction in real world. Okay, so actually. So this thing we say is can correspond to spin in a 3-dimensional real world. So if you have a spin of 2 dimensions, we think that it's actually a point on a bloch sphere. So meaning that spin can point in either direction. So if it point up, then it's the state of this z-axis. It's the state of the z-axis bloch sphere, and if the spin is point down, and you will correspond to a bloch sphere being this one state or point down. Okay. And so we think about in quantum physics, a spin is a 2-dimensional state that can be 2-dimensional state that can be represented as either 0 and 1, and 0 and 1 is represented by the spin being point up or point down. So a spin is like a small magnet, and so the magnet can point up or point down. And but the weird part is now the bloch sphere also represents the spin pointing in all other directions. So maybe the spin want to point in x direction, then it will be the plus state, and or this minus state, or it can point in this y direction, will be this plus y state or minus y state, or in any direction. Okay. And yeah, so a bit of marketing for next class. And but we see that if you think about a spin as some state on the bloch sphere, then weird thing happen, because you think about you have a spin in x direction, and what happen in you measure in z direction, then yeah, then we'll see the quantum physics rule, getting the measurement rule, getting workout on this bloch sphere and real-world spin. Okay. And yeah, so this thing is something that people actually do experiment on and confirm that confirm that quantum mechanics actually happen, and that's the Stern-Gerlach experiment. Okay. This will probably be the most physical part of this course, and yeah, we'll go over this next time. And oh, sorry, a bit like 5 more seconds. And I think I will actually add a bit extra slide at the end of here. Like we also want to talk about QKD at probably after Stern-Gerlach experiment. Okay, so I will update the slides hopefully in next 2 days, and we'll talk about QKD. Okay, so yeah, see you on Thursday, and we'll talk about Stern-Gerlach experiment.